It's quite a rainy day, isn't it? It's been pouring for a while now, and you notice many puddles around your house. And one specific puddle catches your eye. A circular puddle whose radius is expanding at a rate of 1 block per second. You're curious and want to know how fast the area of the puddle increases when the radius is 5 blocks long. If you've ever asked this very specific question, and albeit a strange one, you're in luck, because this is one of the most common questions you'll run into when studying related rates, and that's the topic we're going over today. First, what is related rates? What does that even mean? Well, based on the name, it means to find a rate of change based on another. We can do this through the relation between two rates, hence the name. Let's go back to the puddle problem. What if instead I asked you what the area of the puddle was once the radius became 5 blocks long? Then that would be a very simple question. You just use the area equation for a circle, a equals pi r squared, and plug in the radius to get the area. Well, related rates is actually just a step further than that. Instead of finding constant values, we actually find the rates for those values. So you'll notice a lot of parallels between these two. Now, based off of that, our first step for any related rates problem is to find the equation that establishes the relation. For the puddle problem, our two rates are the area and the radius. So for now, find the equation that relates just the area and the radius. That is going to be the circle equation that we used earlier, the area of the circle. A equals pi r squared. Since we want to find the rates of the area and the radius, our second step will be taking the derivative of the whole equation. Well, what do we take the derivative based on? The area? The radius? Well, it's actually neither. When we refer to questions like these, we are asking the rate of change over time. You can see this based on the fact that the radius increases at a rate of 1 block per second, which refers to time. So we actually take the derivative with respect to time. Now for time I'll be using t, so the derivative of a is dA over dt. Now going on to the other side, the derivative of pi r squared is going to be 2 pi r times dr over dt. Now this is due to implicit differentiation, and so now we have this equation. Okay, so this equation actually has 3 variables. Our third step is now to plug in all the values. Reading the problem, we see that the rate of change of the radius is constant at 1 blocks per second, so we plug that into dr over dt. Now the question asks what the rate of change of the area is once the radius hits 5 blocks, so 5 is going to be our r. Now the last step just involves us solving for a, which gives 10 pi as our answer. So the area increases at a rate of 10 pi blocks squared per second when the radius is 5 blocks long. Okay, that wasn't too bad. Now let's move our sights from the outside to the inside now, with a classic problem involving a ladder. A 15 block ladder is resting against the wall. I push it towards the wall at a rate of 2 blocks per second. How fast is the top of the ladder moving up the wall when the ladder's base is 7 blocks away from the wall? Now there's a lot happening in this problem, so let's actually picture the ladder first to simplify things. The ladder will basically look like this. And you'll notice that the ladder, the wall, and the ground make a right angle triangle. So based on the right angle triangle, the equation to relate all of these sides is going to be the Pythagoras theorem. X squared plus y squared equals z squared. So the first step is done. We then take the derivative of the equation for the second step. But this is actually where a lot of people get tripped up. Now it seems like just taking the derivative of all 3 of these variables works, but one of these variables actually don't belong. And that is actually the hypotenuse, or z squared. Why is that? Well, in the ladder problem, when the ladder is being pushed up, both the x and the y change in length. You can see that because as the ladder's base gets closer to the wall, the x gets smaller and the y gets bigger. But the z is different. The z is the length of the ladder, or the hypotenuse, and that always stays the same. The ladder's length does not decrease as you push the ladder up the wall. So z is actually not a variable at all, and it's just a constant 15 blocks. So our actual equation is x squared plus y squared equals 15 squared. Now taking the derivative of this, we just take it again with respect to time, or t. This gives us 2x times dx over dt plus 2y times dy over dt equals 0. Now the value we're still trying to find is the top of the ladder speed, or dy over dt. we know dx over dt and x, but y is actually still unknown. Now we can actually just find the y value by using the Pythagoras theorem normally. You'll notice that we have the hypotenuse and the x value, so we just do 7 squared plus y squared equals 15 squared. We then isolate y, giving us the square root of 15 squared minus 7 squared, which is about 13.266. With this number, along with x equals 7 and dx over dt equals negative 2, negative 2? This is because since we're pushing the ladder towards x equals 0, we're going in the negative direction. That was just a side note. Anyways, we can plug all of this into the equation we made earlier, giving us 2 times 7 times negative 2 plus 2 times 13.266 times dy over dt equals 0. This can be rewritten into 28 equals 2 times 13.266 times dy over dt. And dy over dt will then equal 1.055 blocks per second. Now the direction is correct since the ladder is going up while the base is going in, so they produce opposite velocities. Since the base is negative, the y value will be positive. And that's all there really is to it. To recap, find the equation that relates to two variables, take the derivative of the equation and plug everything in and then solve. Now for one more general tip, if you're taking AP Calculus or any earlier calculus class, there'll always be two variables like no matter what. You can see this in the ladder problem. If you didn't sub in the ladder's value for the hypotenuse, you would have had 3 variables with the extra z. This is a very clear sign that you're going down the wrong path and you're likely missing some part of the puzzle, so you should definitely go back and check. You can see this in another problem that can trip people up, which is the cone problem. It'll involve the cone being filled up with water and to find the rate of change of volume at a certain height or radius. The thing is, if you're not careful, you'll end up having 3 variables, the volume, the height, and the radius. So you have to realize that the ratio of the height to radius on a cone is always the same no matter what level it's at. So this can be used to substitute one of the values to eliminate a variable. This is the part in related rates that a lot of people get wrong, and it can be very tricky. So if this is something you want to see more in-depth knowledge on, feel free to comment and I'll try to make a video on that problem. Anyways, I hope this video helps. Best of luck with your studies, and bye bye.